Hello, everyone. This is a basic solar car suspension design. I'm going to go over the basics of what you need to know and then kind of more into not so much benchmark, but just knowing what the parameters are don't often let you know what you should set those parameters to. So I'm going to try and shed a little light on that without dictating any designs. Okay, so let's go into the very basics of car suspension and what the different parameters are called and what they mean. So the first one to go into is camber. So this is a view from the back of the car or the front of the car, doesn't matter, but it's not an overhead view. So can you see my pointer?
Yes, we can. Pointer.
Okay, good. So this is an upper suspension arm. This is a lower suspension arm. And we'll call this piece here an upright, the piece that the wheel is attached to. So a car that has positive camber has wheels leaning outward. You'll probably never see a car with positive camber unless it's been involved in an accident. This car has negative camber. That is typically the camber that you would want to see on a car. Now, when I say a car, I mean a road-going production car. For a solar car, you would want to stay with zero camber. And the reason for that is if you think of this as a bicycle wheel, which actually solar cars, many of them have a round cross section similar to a bicycle wheel. As you lean a bicycle wheel over, it's going to turn to that side. And that's just from a very simple phenomenon called camber thrust. And on a simple level, you could say that it is because if you were to have a ground plane here that is deforming this side of the tire, you're now essentially making the radius of this side of the tire shorter than this side. So it's like rolling a cone. If you roll a cone, it's going to go in a circle. So it's going to go this way. So this is camber. It's just how much the wheel is leaning in or out. Okay, caster is a little harder to wrap your head around, but it's basically tilting back. Most cars use positive caster. So you'd be tilting back the steering axis. So this just means if you take the attachment points, typically ball joints at the top and bottom of the upright here, these 2 points, if this one is behind this one in a fore aft sense of your car, then you wind up with positive caster. So your upper ball joint would be here, your lower ball joint would be over here. And by tilting that steering axis back, you're going to have some phenomena that are good for your car. So it's going to increase the steering effort. So it's going to make it harder to turn your steering wheel. However, you're actually going to get steering feedback. And what I mean by feedback is the driver is going to feel how much traction the wheels have that are steering. It's also going to self-center. So you can let go of the steering wheel and the steering wheel will come back to center, which is something that any production car does. The steering wheel is going to naturally return to center. If you don't have that, it's going to feel kind of spooky driving a car that doesn't return to center on its own. And it's just not safe to drive a car that doesn't return to center on its own. Now, having positive caster, like this, actually increases your negative camber through steering angle, as in when you steer the front wheels of the car, if you have caster, your outside wheel, the wheel on the outside of the turn, the one that's taking more load because of weight transfer, that wheel is going to actually lean in a little bit if you have caster on your car. Okay, we'll get more into that later. Okay, toe in and toe out. On the left, we've got toe in. It's just like if you were standing there with your toes facing each other, your toes are pointing in. and here your toes are pointing out. Fairly simple. Most production cars run toe in or zero toe, where they just have the wheels pointing forward. Pretty much no car is going to run toe out unless it's a race car. Toe out helps a car turn in very quickly, but it makes it very unstable. And toe in gives a car stability because in this scenario, you've got both wheels turning in the exact same amount. So this wheel is going to be trying to go this way. This one's trying to go this way. They counter each other. The car goes straight. If in a hypothetical situation, you had a side wind coming at the car from the left, it's now going to cause the car to lean over onto the right wheel, which will give this right wheel more normal force. It gives it more traction, and your right wheel is trying to push left. So it is going to push left, which is countering the force that's pushing the car that actually is pushing the car to the right, which should keep you going straight. So this is good for a production car, but it wastes energy. Those two wheels are constantly fighting each other. So in a solar car, you probably want to go with a zero toe car. You want to have your wheels aligned perfectly straight. And it's going to make the car less stable, but it's going to make it more efficient. Okay, now rod ends. This is a rod end. It's a threaded rod, and there's a ball bearing or a spherical bearing. So you can use these to mount your suspension, like here and here and over here. Now, rod ends should not be loaded in bending if you can avoid it. And if you can't avoid it and you load a rod end in bending, make sure you do the math on it to show that it will survive. And I'll get into where you can find that, an example math problem of that later on our website. So try not to put rod ends in bending. This particular lower A-arm has a shock mounted nearly in the center. It is a little bit more outboard than the center. The center might be here. Ideally, this shock would be placed more over here. And if you could place it over here, you would have much less bending load on the inboard mounting points. And in that situation, kind of like this, if you move this over, I would be fine with these tie rod or these rod ends being in bending over here. They'd have very little bending force if this shock were over here. However, as it is, I would not be happy with these rod ends in bending. Regardless, this one out here on the A-arm that has the shock attached to it is going to be loaded in bending, and it's going to have a fair bit of bending force on it. And that is not a good idea with a rod end, because this part here is not made to be loaded in bending. So an alternative to using a rod end at the outboard side of the A-arm that has a shock on it is something called a spherical bearing, which you'll notice this looks very similar to this. It just doesn't have this part over here that isn't supposed to be loaded in bending. So when you design your upright, or I'm sorry, your A-arm, or either one, you would make an enclosure, a round enclosure, press fit this in, and have a snap ring on at least one side, either a shoulder or a snap ring on the other side. Ideally, a shoulder on one side and a snap ring on the other side. You can't just rely on friction to hold these in. By the rules, you have to have a positive engagement, such as a snap ring. Another solution or another alternative to a tie rod end would be a clevis bushing. So if you just had a tube in your suspension and you put maybe some Delrin bushings or bronze or whatever in there and put a bolt through it. So that works pretty well. It's a low-tech solution. That works well until you get flex, such as if these ears here, you see there's an ear here and one there, another set back here. Those are all attached to this tube. these are not very far from frame nodes, which is good. However, if these were farther from frame nodes, that tube could actually bend. And then you wind up with the axis that this bolt is on, not aligning with the axis that this bolt is on. And then you wind up with binding in this scenario where you're just relying on it to rotate around a bolt. Okay. Built-in adjustability. I would really stress on any car, especially cars for teams that are just starting out, or for people that are starting into even a team that is established. And really anybody, any car, make sure you have adjustability in your suspension. And I don't mean just the capability of adjusting your camber or adjusting your caster, but I mean the capability of adjusting parts from where you intended them or where they wound up after manufacturing to where you wanted them to be after manufacturing. Because tolerant stackups don't always work very well. Parts aren't always made to the right dimensions. Sometimes mistakes are made. So it's nice to have enough adjustability in your parts to actually make everything kind of work the way you wanted it to work. So if you build in adjustability into your parts, you can use less precise manufacturing methods. It's easier to align your car. If you have an accident and you damage some suspension parts or your frame, if you have enough adjustability in your parts, you might be able to still make your suspension work even after that damage. At a minimum, I would make sure that you can adjust your toe and your camber. Now, one thing to be careful about is if you build an A-arm with a rigid outboard structure, say you weld these two tubes together, and then you put rod ends on the inboard end here, as you thread these rod ends in and out, this distance A is going to change. And if that's attached to a frame, well, those 2 points on your frame aren't going to change distance. So you need some provision to allow that adjustability. So one way of doing it that Kentucky has used, and I've seen this on some other cars, but Kentucky has a really nice image of this that I asked them if I could use, and they said yes. They actually have a pinned connection here. This is free to rotate. So this link here can actually move back and forth like this, which allows this distance to change. These 2 points here and here are attached to their frame. This is their lower A-arm, and this point here, and then the one hiding behind the shock, that's their upper A-arm. This linkage out here is the one that actually steers the wheel. It's attached to this rod here. And this linkage here goes to their belt crank and to their shock. So this actually uses a pull rod instead of a push rod. This is in tension, which is a good idea because things in tension don't buckle. Another thing to notice is they use a spherical bearing here with this rather ingenious method of still being able to adjust the length of these linkages so they can adjust where this point is in and out or back and forth to adjust their camber or caster without having to use a tie rod end on the outboard side because it's bad to load a rod end in bending. So, okay, another important thing, design to reduce flexing, but assume that it's always there. Triangulate as much as you can. Like triangulation really is your friend. If you had a frame like this, yeah, there's a lot of metal in there, but there's nothing reacting torques. Like if I wanted to push this way and this way, it would be pretty easy to do, or at least relatively easy when compared to a frame like this. So putting in some triangulation is a really good idea. Notice these are supposed to be A-arms and these are tires. This is my rough Microsoft sketching. So note that the A-arms tie into frame nodes. Node, 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 node. You want to tie into nodes. Otherwise, if you put these mounting points, which have a lot of force going into them, in the middle of a span, that's going to load that tube in bending. And bending is the least efficient form of loading. Tension and compression work well. Bending, you have to have a pretty meaty thing to react to bending. So loads into nodes, triangulate, assume things flex. And I went over this earlier, where if you have bolts going through here, or like a clevis, you need to make sure that this actually is aligned with this, and that it still will be after things flex. Once you put load on them, if those aren't aligned anymore, it's going to bind. Okay, spring and damper mechanical advantage curves. So this is, I think I can reduce this down to a fairly simple concept. We've got suspension arms here, upper arm, lower arm. This is the shock, there's the upright, wheel attaches to the axle. So this shock here is at 35 degrees from vertical. So as we put force on this, it's going to give us a force back. It's going to resist. Let's go over here. As this moves up, the shock angle is going to change. Now it's 46 degrees from vertical. So its force is exerting, it has more of a lateral component and less vertical component. So we're actually gaining mechanical advantage on this shock. Or you could say that the shock is getting weaker as it goes upward, which is not something that you want to have. It's better to have shocks more vertical. However, the counter argument to that is, if you were to be using a spring and damper setup that has rising rate springs, then it might not be a bad idea to counter some of that rising rate with the shock leaning in a little bit. Or if you're using air shocks, which I actually advise against, but a way of using air shocks and getting away with it is to have this decreasing rate geometry. Now, the reason I personally am not a fan of air shocks, years ago, I did Formula SAE in my undergrad, and I used air shocks and they just didn't work well for my team. But one of the reasons they didn't work well is it's very hard to adjust your pressures in your shocks without also affecting your ride height. And ideally you would change your pressure just to change your spring rate. But if you're also changing your ride height, then you're actually adjusting the corner weights on that corner of the car. You make it so that that wheel is not pressing down as much as the other wheels, or it's pressing down more than the other wheels. So you wind up with weird forces going on in your car, and your frame isn't happy, and then you've got to redo all your corner weights, adjust your ride heights at all four corners, and you just wind up chasing a good alignment for a long time. It makes it so your system is too coupled. The other reason that I was not a fan of air shocks is they have this really steep climbing rate here. So as you're pressing on the shock, this is the travel of the shock, and this is the pressure inside the shock. So kind of analogous to the spring rate. So as you've gone about 3/4 of the way through the travel of spring shock, everything is behaving linearly, and then suddenly your spring rate starts climbing very quickly. So it can almost feel like your spring rate has gone to infinity, or you've run out of suspension movement, and you wind up with some spooky behavior in your car. Okay, the placement of your suspension affects loads into your frame. Now I'm going to go back to this. This is what I would consider a quote unquote traditional or classic solar car suspension, where for years solar cars were just kind of a wing with wheel fairings that came down. And so the suspension arms hit up inside that wing, which was pretty high up away from the ground. So you would have this lower suspension arm is actually above the center of the wheel. The axle here isn't even in the picture, it's way down here. So because you have these two suspension arms so close together, the forces on these are really high, because you've got to keep in mind the forces going into this system aren't happening up here or even at the axle. They're happening way down at the contact patch. So if you look at this, let's imagine we're sweeping here. As you're sweeping, use this hand, or yeah. If I kind of did these backwards to how you would think about it. Okay, so you're actually going to be pressing this way and pressing this way, and the broom is going to be moving this way, but the ground is going to be pressing on the broom this way. So just bear with me here. I'm actually making a point here. If you move your hands close together, now imagine moving your hands closer together like this, you're holding them here. You would have to press pretty hard with your two hands to actually sweep with the same force going across here. And it's the same thing with the suspension on a car. If this is your upright, and here's your axle, and here's your wheel, if you've got your mounting points here and here versus here and here, or at the extreme here and here, the amount of force that you're going to have to put on these 2 points is ridiculous, because you're reacting a torque being created by this force here. So this force is going this way. You've got your lower A arm is going to push out, your upper A arm is going to pull in, which may seem counterintuitive, but your upper A arm is actually pulling in. And the closer you have those together, the higher those forces are going to have to be to react to this torque. So a better solution would be to have those mounting points as far apart as possible. And if you look at a production car, this is what you're going to see, where just about every race car that uses a double A-arm suspension is going to have the lower ball joint way down here and the upper ball joint way up here, or some even higher. Since they're outside of the tire, they can actually even have them up here. So the reason that I mentioned this is if you have lower forces in your A-arms, you also have lower forces on your frame. Lower forces in your A-arms allows you to make them lighter. Lower forces in your frame allows you to make it lighter. Okay, weight transfer. So weight transfer is a function of CG height and location. I'm sure that's not really news to anyone. But the less weight transfer you have, the better it is for cornering. You can tell me theories either way about how it affects braking, but you need to account for this in your braking and your cornering load calculations. So in your VDRs or your PVDRs, when you say, we think that our suspension will be able to take the loads from cornering and braking, well, I want to see the math of why it can take those loads. And ideally, I would like you to take into account weight transfer when you do that math. So lateral transfer, as in when you're cornering, weight transferring from the inside of the car to the outside of the car, as in you're your wheels on the outside of the turn now have more load on them. So how much more load do they have? What is the new normal there, the new normal force? So when you're doing the cornering calculations of can your suspension take this, it's more realistic to actually say we have this much force on our wheel, taking into account weight transfer, than just saying we have 1/4 of the weight of the car on each wheel. And I'll go off on a slight tangent here. It's one of my pet peeves is when I'm reading a report and no center of gravity location has been named, but the team just says, we'll assume that 1/4 of the weight of the car is on each wheel for these calculations of cornering forces and braking forces and bump. But that is a best case scenario. Like if you can build a car where exactly 1/4 of the weight is on each wheel, you've done really well. And in theory, your car would handle pretty well. But unless your car has a center of gravity at ground level, which we all know is impossible unless it's just a sheet of paper, you're not going to resist weight transfer to your outside wheels in cornering or to your front wheels in braking. So your wheels are going to wind up with more than that 25% in a dynamic situation. So I'm not going to go through these equations. You can kind of derive these equations yourself or look these up. But basically what these equations say is here's the new weight when you're cornering. So the weight on this wheel is going to increase if you have a vector going, if the wheel is creating cornering force and the car is going this way.
Out of curiosity, if you were to raise your center of roll to the height of your CG, theoretically, not that this would be a great idea, but would that also combat the weight transfer?
No. Raising your roll center to your CG doesn't actually combat weight transfer. And I've actually heard that can actually cause more weight transfer. Like weight transfer really is just as simple as where's your CG and where does it's where's the CG and how much force is on it. And actually to get slightly more in depth, the reason I say it can cause more weight transfer is when you have a higher roll center, it can actually cause jacking forces. And if you had your roll center all the way up at your CG, it probably would cause a jacking force. So the outside of the car would actually tend to move upward. And since you're moving the outside of the car upward, the whole car is going to move upward. And now you've raised your CG. And as you raise your CG, you're going to wind up with more weight transfer.
That makes sense. Thank you.
I'll get into roll centers a little. I'll skim over roll centers in a bit here. Okay, so basic suspension analysis in the VDR. I want to see something like this. This printout here, this is a PDF that's actually on the site. If you go to the American Solar Challenge site, under regulations, there's Solar Car Design Reference Manual. And then down here, front suspension static analysis. And then this is there. And it actually lists all the equations. I only showed the fancy picture part, but there's all the equations underneath. If you have a rod end and bending, the sample analysis for that is here, rod end stress calculations. Okay, on to this. I would like to note that when I first saw this was actually put together by Dick Roberto. And when I first saw it, I thought there was a mistake until I reasoned through why he would have done it this way, because Dick Roberto is a very smart guy. And I figured it out and I asked him and he confirmed it. But something to keep in mind, this analysis is actually done for the inside wheel of a car, which coming from the Formula SAE world seems counterintuitive to me, because in Formula SAE, you really only care about the outside wheel. That's the important one for the geometry and what is outside wheel doing, because that's taking a lot of load, because in Formula SAE, you're trying to corner as high G as possible. So you wind up with a lot of weight transfer to the outside wheel, and the inside wheel is just kind of along for the ride. However, in solar car, that isn't necessarily the case. But the reason that I see to actually look at the inside wheel is because the loading in theory might actually be worse on the inside wheel than the outside wheel. And let me briefly explain why that is. So if you put your traction force here, so this is your cornering force at the bottom of the tire. This is the tire, here's the rim goes up to the axle. So here's the bottom of the tire at ground level, and you've got your force going this way, which would make this the inside wheel of the car. So the inside wheel has the force going this way, your normal is going this way. In this situation, if you were to sum torques around this point or this point, your normal is going to create a counterclockwise torque around either of these 2 points. Your cornering force is also going to create a counterclockwise torque around these 2 points. Now, if this were the outside wheel, your cornering force would be going inward. That would be creating a clockwise torque, which would be counteracted by this normal here, which because of weight transfer, that normal has increased. So you now have a normal here that is counteracting your cornering force by its counterclockwise torque. So the outside wheel actually has those two torques kind of fighting against each other and creating less force up here. But the inside wheel actually has more force. So I would suggest you calculate the loads. Now it's going to change with whatever your geometry is. So it could wind up with you have more force more forces in your A-arms on your inside wheel or your outside wheel. But I would suggest actually doing the math on both of them and use the corrected normals. So when you're looking at your inside wheel, it does have where you have two torques that are adding, but you also have a decreased normal here. So if your center of gravity is pretty high, you may have enough weight transfer off of this wheel that it's actually lower forces than on your outside wheel. So it's going to depend on your center of gravity height and your geometry, but it would be a good idea to do the math both ways or the math for both wheels. Okay, now something I mentioned before, I'm going to mention again here. Bump, cornering, and braking forces are input at the contact patch, not the axle or center of the wheel. And what I mean by that is these forces go in here, and here's your braking force at the contact patch here. I've seen many teams try and put the forces in here at the axle, but that doesn't really capture what's actually going on here. Okay, designing suspension parts for loads. You're just going to design your dynamic loads as static loads. And by the rules, we require that you apply a minimum of 2G in bump, as in pushing the wheel up, 1G of braking, 1G of lateral force. And I would like you to do that with your suspension loads, including weight transfer. As in, like I just explained a minute ago, the 1G of lateral force. For your inside wheel, you can decrease the normal, but for your outside wheel, you should increase the normal. For braking, for your front brakes, take into account that you're going to have weight transfer to the front of the car. So you're going to have increased normal up there too. Now, this 1G lateral force, keep in mind that in 2019, was it? Yeah, 2019 at Circuit of the Americas, Kentucky's car rounded the track in, I want to say 3 minutes, 41 seconds. Somebody can correct me on that. They said a blistering pace. And at points they were cornering at over 1.4 Gs. So if they had built their suspension to 1 G of lateral force, their suspension would have failed. So this is just a minimum. Okay, place input forces at contact patch. I know I've said that before, and I'll probably say it 3 or 4 more times. Analyzes the static problem with 3 torques and 3 forces. And then once you have found all those forces and torques, pass them on to the next part. Don't just say, okay, my A-arm is going to pass, or don't just go, oh, my upright is good, it's passed those forces onto my A-arm, I'm done. Like, you need to analyze from the tire into the hub, to the upright, to the A-arm, to the frame. And once you're to the frame, determine if your frame is going to be able to handle those forces. We have seen frames fail where the suspension is attached. If your frame is going to fail, that's a likely place for it to fail.
Hey, Bill, for those suspension loadings, would you say teams should be analyzing that at combined loading condition, or just one at a time
Yes.
is fine?
Yes. Actually, I would suggest doing it both ways. I would suggest doing it, and actually by the rules, you're supposed to do combined, where you got the 2G, 1G, 1G. But I would also suggest doing them separately, just as we noted how you had the torque from the normal. The torque from the normal here is going to give you a counterclockwise torque. But if you have a torque from cornering coming in here, giving you a clockwise torque, that kind of counter each other. And then you could go, well, if I just put this into 2G bump going this way, then I can take a whole lot of G's cornering this way and everything's fine. Well, it could happen that if you have that 2G bump and 1G cornering and 1G braking, everything works fine. But if you take away your 1G braking, then your suspension actually fails. And that may seem counterintuitive, but that 1G of braking or the 1G of cornering may have actually been helping the other loading. Okay, so your brake performance analysis. What I kind of want to see in the VDR is, will your brake system survive, and will your car survive your brake system, and will your car actually be able to perform at the level that we require it to perform at to pass dynamics. So in dynamics, we require that your car can stop at 4.72 meters per second squared. So to get your car to stop at that acceleration, how much pedal force is required? Now, production cars are going to take between 70 and 100 pounds of force at the pedal, like your foot pushing down on the pedal, 70, 100 pounds of force to do a panic stop. At that point, you're probably going to be at the point where you feel the ABS pulsing. So I would hope that when you do the math and say, well, when our car is decelerating at this rate, you don't wind up with numbers like, we need 300 pounds of force on our pedal to achieve that. I also would hope that you don't wind up with numbers like, we need 11 pounds of force on our pedal to achieve that. Because then you could actually wind up in the scenario where just the weight of a person's foot, like you initiate the stop, and then the deceleration of the car is pushing their foot into the brake pedal, and you wind up with kind of a divergent situation where, or convergent, where the person's foot is creating more braking force. And it's also going to be hard to modulate brakes that react too easily. So it's going to be hard to keep those brakes from locking up. And if they do lock up, to unlock them and get back to that sweet point. Okay, another question to answer is, at what point do your front wheels lock up? Is that pedal effort discernible from the required force to generate 4.72 meters per second squared of braking? So if you take 50 pounds of force to get your car to stop at that speed or at that rate, but it only takes 60 pounds of force to lock up the wheels, your driver's going to have to be very good to work in that sweet spot. At the point where the front wheels lock up, have the rear wheels locked up yet? And the reason this is important is when wheels lock up, they lose the ability to generate lateral force. And when I say lateral force, I mean side to side force, as in a wheel that has stopped rolling does not keep itself from sliding sideways. So if you have the rear wheels of a car lock up, it has now lost its ability to keep itself from sliding sideways. The front of the car still has braking force, and any imbalance in that car, as in if one of the front wheels has more braking force than the other, or if the center of gravity of the car isn't perfectly centered between the front wheels, or there's a slight side wind, anything can create an imbalance, and it really doesn't take much. It can cause the back wheels to slide to one side. And then once they start sliding to one side, you've already created a yaw situation, and it's not balanced anymore. The CG of the car is trying to go forward past the front wheels, and it's already gotten out to the side. It's just going to keep going. It's going to pendulum around the front wheels because they have a drag force on them. They're pushing back, the rest of the car is pushing forward. So the part of the car that's pushing forward, the center of gravity, is just going to go past the part of the car that's pushing backward, the front wheels, and all of a sudden you've spun your car. And that is why we don't want your rear wheels to lock up first. The front wheels should always lock up first. Another thing to check for is if you put 200 pounds of force on a pedal, which is not hard to do, especially in a panic situation, if you think you're about to hit something, what's going to happen to that pedal? And I mean the pedal itself, the pedal arm, the pedal, the hydraulics down there, that area of your car, whatever your pedal is mounted to, is it going to break? We have had failures over the years where the actual pedal arm or the mounts break. So don't be one of those teams that kills their pedal in dynamics. Okay, now I put this page together as kind of a sample page. I'm not going to go through this one by one. I'm hoping that you guys can pull up this presentation later and look at this. If you want, you can email me and I will email this back to you. But this is basically kind of some rough calculations. It's not the only way to prove to me that your brakes will work, but it is a way of doing it. Okay, now camber gain from bump. If you remember back from one of the very first slides, camber is how the wheel is leaning in or out. This is a view from either the front or back of the car. As these wheels are moving up and down, they're actually leaning in or out. They're not leaning all that much, but if you look very carefully, you can kind of see like a stair step kind of right there. And this one kind of a little stair step. So it is leaning in a little bit as they move upward. And the reason it's good for a car to do that is as these wheels are moving, as this one's moving up and this one's moving down, that would be happening in a corner. So in a corner, the car is probably going to be rolling to the outside. So if you have that wheel leaning in a little bit, that counteracts the roll. So in theory, well, hopefully, your wheel should actually still be pointing up and down, or maybe even a little bit in, or if it's leaning out, it would be leaning out less than it would be otherwise. So camber gain is a good thing. It's enabled by having a shorter upper A-arm. So this one here, note that it is shorter than the bottom one. or by tilting it downward as it goes in. I was hoping eventually this animation would stop. It does when I edit this, but apparently not in the slideshow format. But yeah, if this is pointing downward, you can see how that from rest, if this is pointing downward and this one is level, as this one moves up, the bottom one moves up, it's not going to have much translation in. But since this one, which is already at an angle, is starting to swing more this way, this outboard point is going to move inboard more than this outboard point. So it's going to tilt the wheel in. So the shorter this arm is in relation to this arm, or the more of an angle it starts at, the more camber gain you're going to have. Also, just shortening these arms at all is going to give you more camber gain per amount of travel at the wheel. If you had a really long arm that went all the way over to here or something, you're going to wind up with very little change in the length of that arm, very little translation of the outboard mounting points. So you have almost no camber gain if you have a really long arm. So this is something that you might want to play with as you're looking at camber gain. Just playing with the length of the arms, the angle that it's at, the relative length of the arms. Okay, now something that might actually be more important to think about when you're playing with the length of the arms and the angles of the arms and the rest position of the arms is scrub. So scrub caused by bump, as in this would be the yellow lines would be the arms pointing down when the car is up, and then when the suspension compresses, you have these arms going out. And this is the tire before, and this is the tire after. There's actually a lateral movement of the tire, and that wastes energy. Now, this is exaggerated, but in a solar car, having that tire move side to side is going to waste energy. It takes energy to grind those little bits of tire off. So as your suspension moves through its range of motion, it would be good to try and keep the contact patch from moving laterally. You can have the top of the tire or other parts of the tire move laterally, but try and angle it at different points through its movement to try and keep the contact patch of the tire at pretty much the same point. And that's something where if you just work with modeling software and toy around with your suspension, you might be able to optimize that. Beginning with A-arms that are nearly level will help reduce scrub, because you're going to wind up with, well, when they're level, as you rotate them, you're going to have less translation in a lateral sense than if they were not level to start off with. And longer A-arms may decrease your scrub. So, but keep in mind that longer A-arms also decrease your camber gain. So everything's going to be compromises. Do you want camber gain? Do you want decreased scrub? Okay, now this picture I came across back in 2013. And I saved it away in a presentation and I didn't look at it for a long time. And I thought that this was a trailing arm suspension because that's all I had ever seen with a suspension like this. I could tell that the wheel was pointed this way, suspension arm was doing this way. So that's a trailing arm, right? But it's not. This is actually the front suspension of a car. This is a leading arm suspension, which I just noticed a few weeks ago when I pulled this picture out to make this presentation. And the reason I realized it is because since 2013, I'd say just in the last 3 or 4 years, I have seen several cars that have a suspension very similar to this. And this is a leading arm suspension similar to what a lot of catamarans are running nowadays, which is something that I thought was a totally new idea when I saw it first in probably 2016. But as they say, there are no new ideas, or they say something like that. But this is the lower suspension arm. This is the upper suspension arm. And just like A-arms, you've got the two inboard mounting points and the one outboard mounting point going to your upright here. But it's just turned 90 degrees. And the reason you would do this is behind here is presumably just an air tunnel, just free space where you aren't plowing through air. It reduces the cross section of your car. So in a catamaran, you can run a suspension like this. This bulkhead here is structural, all your suspension is attached to it. And a rather novel thing is this steering linkage arrangement. This rod here moves laterally, goes this way, which rotates this arm here, which rotates this rod. And then this linkage down here will rotate kind of fore and aft, which pushes this rod fore and aft. And presumably there's a lever arm attached to that rod and going over to the upright, kind of back here. And that will steer this wheel. Now, I think this is actually a pretty good design. But one thing that I would definitely not do is don't use bicycle wheels. Bicycle wheels are not up to the task. They are not built for side loads. Wheels with spokes are going to break. You're going to wind up having to rebuild your wheels daily. So do not use bicycle wheels. Natural frequency for determining springs. This is one method of determining springs, and it's, in my opinion, the easiest method. There are other methods that some people could argue are better ways of doing it, but I think this works just fine, especially for solar cars. So take the calculated weight from your axle and determine your spring rate by the natural frequency. So natural frequency is just the spring constant versus the weight. It's going to give you natural frequency. Ideally, your front natural frequency should be a little bit higher than your rear natural frequency. So just take your rear, multiply it by 1.15, or you can work the problem the other way. But that should be your spring rate. Now, that would be the rate at the wheel. So if you have, say, bell cranks multiplying the force, or if you have your shock relatively far inboard on your arm, you're going to have to do the geometry there to figure out what your effective spring rate is at the wheel. So yeah, I would suggest about 1.15, just to give you some kind of frame of reference. Passenger cars are about 1.0 to 1.3, so think like Camry, sports sedans, perhaps BMWs, Audis, they're going to be in the 1.2 to 1.5 range. Sports cars are 1.5 to 1.8. We're talking like Ferraris, Lamborghinis. And actually nowadays, suspensions are softer. They rely more on the damper to control the car. But we'd say 10 or 15 years ago, sports cars are in the 1.5 to 1.8 range. And only dedicated race cars with aerodynamics are going to be over 1.8. So if you have your natural frequency up in the 2 to 3 range, I'm going to say, why are you doing that? And I have said that to some teams that say what their natural frequency is. Typically the answer is, well, we like to control our ride height more closely. So that's why we want very stiff springs. It's like, but that's going to make your car kind of bounce over bumps that it should be trying to absorb. Okay, quick review on Caster, because we're about to get into how Caster affects things. Oh, actually, we're running short on time, so maybe we shouldn't get so much into that. But one thing to go over real quick, caster increases the negative camber gain through steering angle for both inside and outside wheel. What I mean by that is, if you remember, the negative camber is the one that you want. So if you have caster built into your steering, as you turn your wheels, it's going to actually induce camber on your wheels. It's going to have your wheels lean into the turn. Now, to counter that is kingpin inclination. This is the angle. It's kind of like caster, but it's viewed from the front of the car or back of the car versus from the side of the car. So this is your steering axis. And the angle that that axis is from vertical is your kingpin inclination. Now, kingpin inclination is going to do the opposite. The more kingpin inclination you have, the more it's going to give you positive camber gain on your outside, or actually for both wheels. So if you have more kingpin inclination than you do caster, your wheels are actually going to lean to the outside as you turn, which is not going to help. It's going to, since your wheels lean to the outside, it's going to tend to push more to the outside. Your car is not going to go where you're trying to get it to go. Now, KPI is usually necessary to try and get this radius here to shrink. If you had these 2 points just stacked up and you weren't able to tuck them inside this wheel or stack them over the wheel, then you'd wind up with a large scrub radius, and that large scrub radius is going to have bad effects. That's going to create all sorts of forces that are not good that I don't really have time to get into, but it is good to have a smaller scrub radius, although you never want your scrub radius to go to 0. So your scrub radius, this axis here, should not touch the center of the wheel. It can even be on the other side. It's perfectly valid to put the steering axis and hit the ground on the other side here. You can have it over here, but don't put it right there. I would not put the steering axis within a 1/4 inch of your tire center line, because as you corner, the tire itself is going to deform, and it's actually going, say you're cornering, the tire might look more like this. It might come this way, and over here it'd be kind of going this way. So now the center of the tire isn't here, it's over here. If you had your steering axis coming down and pointing, say, there, your tire, the center of your tire was on one side of it, now it's on the other side of it. And the scrub radius determines the feedback that you feel in the steering. So if in the middle of the corner, you're getting feedback in the steering that's pushing one way, and then the tire deforms as it's going to do in the corner, and then you get feedback going the other way, it's going to feel very spooky to your driver, and you don't want that. This is another thing where I wish I had more time to get into, but I don't. So you can look at that hopefully later. And
We've got 30 minutes before we have our next issue, so you can run long if those that want.
Oh, they're not going to kick me off or anything?
I don't think so.
Okay, well, I'll run with it then. Okay, so let me see if I skimmed over. I think I hit that enough. Okay, so I will get into this. And in reality, it would be better to go to my kind of bonus material that I put at the end here. Okay, so I can't actually read the title there, but let's go into a hypothetical scenario here. In this scenario, we're going to have 15 degrees of kingpin inclination and 0 caster stacked right up here. So we have more KPI than caster, which is a situation that I said you should not do. Because caster is going to give you negative camber gain on your outside wheel. So this is what will happen to your outside wheel. As you turn your steering, your wheel rotates forward. See how this axle is pointed downward and your wheel is tilted outward? So that wheel is leaning to the right. It's going to push this way, even though you're trying to get the car to go that way. This is not what you want. The inside wheel is actually leaning the correct way. But your outside wheel, the one with more force on it, is fighting it. It's going the wrong way. So this is what happens when you have more KPI than caster. Okay, so now let's go to a different scenario. Now I went to kind of an extreme here. I'll admit when I built this setup, I was hoping for it to be a little more adjustable and work with me, but it didn't quite work out very well. So I have this set to 25 degrees kingpin inclination and 35 degrees of caster. Ideally, it would have been 25 degrees, but the stars didn't align. So this is the outside wheel, and this isn't viewed from any funky angle. This is viewed from behind it. The outside wheel is lifted way up into the air, which actually, I'm sorry, let me go back to this one and point something out. At zero steering angle, the wheel was level with ground. So I'm calling this black piece of rubber here ground, and the wheel is level with it. However, as we've turned, you can see the wheel has actually moved below ground level. Now, in reality, your wheel isn't going to move below ground level. But what will happen is it will lift that corner of the car. And that is called a jacking force. It's like you're jacking up that corner of the car. And it's something that you can actually see in a production car. Like if you were to sit in your car and turn the key on. If you have power steering, it might be easier to just have the engine going. But if you're in your car, you don't, as in not actually traveling anywhere, just sitting still and get down low enough that you can look at a point, either say your windshield wipers, or maybe if you have a hood that actually sticks out, or a point on the A or the A pillar of your car, and look past that point to a fixed point off of your car. Say like if you're parked next to another car or a building or something, and look at that point and then turn your steering side to side. Turn it all the way one way and all the way back the other way. And you'll actually see how the front of your car, one side of it will go up and the other side will go down. And as you move your steering back the other direction, it'll tilt back the other way. And that's from jacking forces. And those jacking forces are giving you steering feel. Like as you're cornering or as you're turning the wheel, you're actually picking up one side of the car. And the weight of the car is going, no, I don't want to do this. So you're feeling that in the steering. And that's going to help the steering wheel return back to center. So in this situation, we have jacking forces. Now, kingpin inclination gives you jacking forces in both directions. It doesn't matter if it's inside wheel or outside wheel, it's trying to lift both of them. But if we go and look at caster, this is your outside wheel of caster. So we've got 10 degrees more caster than we do kingpin inclination. So your outside wheel at, if you were to turn this a full 90 degrees, it's actually going to be, your axle is going to be tilted up at 10 degrees. At this, it was probably tilted up at maybe 7 degrees, which it doesn't really look like it from this angle, but that's a pretty long axle. So it really is probably only tilted up at about 7 degrees. So that wheel is tilted over, as in it's leaning into the turn. What just happened?
I'm not sure what happened.
Looks like you ended the slideshow.
Oh, you're back.
Okay, let's try that again.
I think you accidentally clicked, and so it took you to the end of this lecture.
Oh yeah, that was the last slide. So yeah, that's probably what happened. Okay, so your outside wheel in this situation is going to move upward, which means it does not have a jacking force on it. It's not going to fight you. But your inside wheel is moving downward. It's got a jacking force on it, but you've got weight transfer off of that. So caster is not going to fight you as far as jacking forces. So the weight of your car isn't going to dictate the jacking forces that are fighting your steering feel with caster, but they will with kingpin inclination, because kingpin inclination is going to give you jacking forces in both directions. And you can play around with these two parameters, kingpin inclination and caster. And I would suggest if you play around with them in your steering system, don't set them to something ridiculous like 25 and 35 degrees. I'd be more in the 5-degree range. But when you play around with them, just check how far does your wheel move in a vertical sense, and that will give you your jacking forces. And then you can just say, well, if we move 1/4 of an inch as our steering moves through this much, well, our actual steering wheel had to move 1 full turn, and 1 full turn, our hands would move this far, and we're going up 1/4 inch. So the work being done over this distance would be lifting the weight of the car, or the weight on that wheel, by 1/4 inch. And you could just do a kind of a, not potential energy, but a work equation to figure out what force is that adding to your steering wheel. The other part of that is, I'll get into the other part of the steering feel thing in a second. Let me go back. Okay. So steering torque is going to be dictated by the jacking forces, which I just talked about. And then something called the mechanical trail, which, oh my, I think I have omitted this from the presentation. But okay, so your mechanical trail is this distance from where your steering axis hits the ground to this vertical line. So that mechanical trail, so your contact, when I say the vertical line, I really mean where your tire hits the ground. So if you imagine lateral forces happening at the contact patch and your steering axis is here, that lateral force at the contact patch is going to create a torque around your steering axis. So let's try and wrap our head around this. Now, I would say close your eyes and imagine this, because I don't have a picture for it. Yeah, maybe closing your eyes and imagine this works better. So if you imagine a bicycle, and a bicycle is going into a turn, and you turn the bicycle to the left, and bicycles have caster, like the front tube of a bicycle where that connects the handlebars to the fork that has the wheel on it, that's going to be tilted back at an angle. So you're going to wind up with that mechanical trail that I mentioned a minute ago. So let's all turn left on our bicycle. So we turn left. As we're trying to turn left on our bicycle, we turn to the left. So the contact patch of the bicycle is going to be, the tire is going to be pushing on the ground. It's going to be pushing the ground to the right. The ground's going to be pushing back on it to the left. So that's the lateral force on the wheel is going to the left. And that lateral force is creating a torque around your steering axis, which is going to the left. Now, for us to go left, we're pushing on the handlebars in a counterclockwise direction. Now, that lateral force at the contact patch is pushing on the wheel around the steering axis in a clockwise direction because it's going to the left and it is behind the steering axis. So notice we're pushing in a counterclockwise, that lateral force is pushing in a clockwise. So it's going to try and bring the handlebars back toward center. The more cornering forces you have, or the longer that moment arm is, which is dictated by the amount of caster you have, because the more caster you have, the longer your mechanical trail will be. But so the more the cornering forces are, or the more mechanical trail you have, make it so that you get more feedback in the steering. And that feedback is going to help that steering self-center. Okay, now that we've closed our eyes, I need to actually, now that we can open our eyes, I need to get back to the right slide here. Okay, so the camber induced by steering that we kind of went over with those slides at the very end of the presentation there. So the positive caster increases negative camber gain through steering for the outside wheel, and it only works for the outside wheel. So caster helps your outside wheel. The kingpin inclination increases positive caster gain, positive camber gain through steering for both wheels. But we also pointed out that it also increases the jacking force on both wheels. And you can actually calculate the camber gain on your two wheels from these equations, inside wheel and outside wheel. These are actually pretty simple equations. And in conclusion, since the negative camber gain is desired for your outside wheel, your positive caster should exceed or equal your KPI, your kingpin inclination. Okay, and we kind of touched on the jacking forces and that those last two slides. That's just basically how much your wheel is trying to move downward through the ground plane, which is actually lifting your car up. And for mini solar cars, especially the cruiser class, like just a single person solar car, you're probably not going to have to worry about calculating jacking forces if you have a relatively light car until you get into higher kingpin inclinations or casters, which is pretty rare to see on a solar car, but it doesn't mean that a first year team wouldn't do that. So yeah, I would not go past more than a few degrees kingpin inclination or caster. And if you do, make sure you're actually doing the numbers on what is my steering feel or what is my steering feedback going to be like, because you don't want to wind up with steering that is too hard to turn. I think we kind of went over this a little bit. Steering torque is affected by the torque produced by the product of the mechanical trail lateral loads. That was our close our eyes and ride a bike thing. Steering motion creating jacking forces. So if you're actually lifting a corner of the car by turning the steering wheel, that's going to be hard to do. But here's something that's going to be harder to quantify: the friction in the system. So if you say have a catamaran car where you have a very intricate steering arrangement, like the picture that we saw that I cannot find now, but here, if you have this very intricate steering arrangement, you have friction there, you have friction there, you have friction there, you have friction there, and up here, and at your lower ball joint, And you have all that on the other side of the car. If there's any other linkages in here. So all those points, you're going to have friction, and that adds up. So that's something to keep in mind when you're trying to figure out how much steering force it's going to take just to get your car to turn. Roll centers, this was touched on briefly. So a roll center is kind of the imaginary point where your car actually rolls about. And when I say roll, I mean how it tilts side to side. This is a geometric way of calculating roll center. There are various methods. There's force methods, but this is a nice, simple way of doing it. So to calculate your roll center, you calculate the instantaneous roll center of one side of your suspension. So if you get this arm, continue it, goes to there. This arm continues, goes to there. And then from that point, you go back to the contact patch of your tire. Now do this for both sides of your car, and where they meet in the center, that's your roll center. Now, if we were to, I think I'm going back too far here. I'm looking for the scrub. Okay. So a car like this is going to have those points going way up. Well, if we had the hypothetical roll center way up, or the instantaneous center way up here, and then you drew a line down to your contact patch, and then your two lines from both sides of the car met up here, and your center of gravity were up here, then your car would in theory roll about that point. And you might say, well, that would be kind of cool to have a car that doesn't roll at all. However, let's look at suspension that is at that weird of an angle. So you've got this really high angle of that coming up and that coming up. You could even drop this down a little bit so that these actually converge at some point over here. But when you have that really high angle here, think about what happens when you put a lateral force on here. So you're putting a lateral force on here. It almost looks like, hey, this wheel wants to tuck under the car. When you come to the point where your roll center is actually above your center of gravity, this wheel will actually tuck under the car. When you try and go into a corner, the wheel will go under the car. And this is actually a problem that swing arm suspensions had back in the 60s. Corvairs and Beetles, various cars with swing arm suspensions would have where either the wheel would tuck under the car and cause the car to jack up and then raise the center of gravity really high and cause the car to roll over. And when I say roll over, I don't just mean rotate, I actually mean shiny side down. So having a suspension where you have the roll center too close to the center of gravity, too high up, can actually kind of shoot you in the foot. It's something that when you first learn about roll centers, it's very tempting to do. And I'll admit that when I first learned about roll centers, I said, wow, I can eliminate anti-roll bars. I can just make it so I can have the car lean almost not at all. This sounds like the Holy Grail, but it really isn't the Holy Grail. And most sports cars have a roll center right around ground level. Some actually have the roll center below ground level. So back to, okay, so that was roll centers. Try not to have the roll center migrate through the ground plane. When I say migrate, I mean as you move your suspension, as this goes up, these angles are going to change. This instantaneous roll center might move down here. And when it does, this line drawing over to your contact patch meets the other line for the other side under the ground. When it goes from above ground to underground, you get spooky handling. So I would keep it low, but not too low, not right at ground level, because then it might actually migrate through ground level. It helps to control roll centers if your lower A arms start off nearly horizontal, which I think is something that I've said a few times during this presentation for other things. Just having your lower A arms starting nearly horizontal helps in so many things. Shallow angles for your upper A arm also help lower your roll centers, as in having this A arm point downward. That's going to make it, if you start off with, say, this level and this points downward, you're going to wind up with your instantaneous roll center way over here. And the further away it is, the less it's going to migrate. I would start modeling by picking a roll center height, as in how far off the ground do we want it? And then that's going to give you, and then pick a instantaneous center location, say how far over here do we want it? How stable do we want our roll center migration to be? And then from there, that can dictate where your arms are. And keep in mind your arm lengths. You're also going to want to take into account how much camber gain you want when you do your arm lengths. Ackermann geometry. So Ackermann geometry is something that was actually created before cars existed. It was for horse-drawn carriages, and the person that created it did it at the wishes of a wealthy landowner that was sick of seeing wagon wheel ruts in their dirt driveway, and they wanted it to turn more efficiently. So Ackermann figured out, actually, I think it might not have been somebody named Ackermann. Ackermann may have been the person paying for the work. But in short, this is the geometry that they came up with, and it works. So if you go through the steering axis and the outboard tie rod mounting point, and you have that line meet at the center of the rear axle, everything works beautifully. The outside wheel traces a circle, the inside wheel turns more, it traces a tighter circle, and everybody's in agreement and everybody's happy. This works very well at low speeds. At high speeds, it gets more complicated, because at high speeds, each of those wheels are actually slipping, as in the direction it's pointed is not the same direction that it's traveling. And the more load you have on a tire, the higher that slip angle can be. So you can actually wind up with this tire is pointed this way. If this tire is turned more, you would say, oh, that's a good thing because it's turning on a tighter circle. But if this tire also has less force on it because of weight transfer, then having that angle, this angle be higher, might not be sustainable. The tire might just say, oh, I don't have enough force on me to sustain that slip angle, so I'm going to let go and give up and not give you any traction. I'll just be a drag force. So this is something that I think might be worth studying for some teams that have already got the rest of their suspension figured out. And you can actually adjust the Ackermann of a car, not just by moving these 2 points in and out, but also by having your steering rack, which sits in the center here, move it fore and aft in relation to your outboard mounting points. But that's getting into like the 400 or 600 level class type stuff. This is another example of Ackermann. You'll notice that the steering axis, well, the upper ball joint is there, lower ball joint is there, so the steering axis is going down. So at the level that this arm is at, steering axis is probably about there. And then their tie rod point is there. And keep in mind, this is actually pushed out a little bit because that wheel is rotated in this way. It's been rotated clockwise. So at rest, this point would actually be more in here. So that line probably goes about this way. And it's going toward the center of the car. So they've got Ackerman there. There's also, while we're at it, redundant brakes. It's a good thing.
What is the application of an anti-Ackerman geometry?
Anti-Ackerman, Formula One cars typically run anti-Ackerman because they'll have enough weight transfer off the inside wheel. And that weight transfer off the inside wheel is making it so that it can't sustain the slip angle. But also Formula One cars have a really long wheelbase. So like a traditional Ackerman, once that wheel starts slipping, like if you had a very wide car compared to how long it is, once that wheel starts slipping, then you could say, oh, well, it's not such a bad thing because now it's generating a drag force on the inside. So it's helping the car pivot. But on a Formula One car, the lateral component of that, like since it's a narrow track compared to how long it is, it's pretty far from the center of gravity. So they would value having the cornering force on that front wheel because the moment arm, if you put a lateral load about the center of gravity on a Formula One car, a relatively long wheelbase car, that long moment arm joined with that lateral force is going to put more torque on a car than if you were to put a drag force on that wheel where it only has a moment arm of half the track, half the relatively narrow track, and it's just a drag force. So that's why Formula One cars, they'll actually run an anti-Ackerman to try and keep that inside wheel actually still generating some cornering force, even though it has a reduced load on it. Does that make sense?
Gotcha. Yeah, that does make sense. So it's not so much a function of the speed of the event, but more so the wheelbase geometry of what they're doing.
Correct. Yeah. I believe wheelbase geometry is the largest driving force of why you would want to choose anti-Ackerman over Ackerman or under Ackerman.
Thank you.
Not a problem. Okay, so bump steer. I think I'm about to run out of time here, but actually let me make sure there's nothing else that. Okay, so yeah, bump steer I think is the most important thing that I have left that I have not covered, because this is something that when I see it on cars, I'm like, oh God, you've got to change this. So bump steer is where your wheel moves into bump, and it could be from hitting a bump or it could be from cornering. It could be that your car is cornering, it's leaning to the outside, so this wheel is actually moving up. It could be from braking, so both front wheels are moving up. But it's basically when your wheel moves into bump, if that makes your car steer, then that's bump steer. And the way you get bump steer, which you do not want, but the way you would get it is if your tie rod is too long or too short, or if it's at a funny angle. So how you prevent it is you have it the correct length and you have it at the right angle. And how you do that is you actually make sure that your upper A arm, your lower A arm, and your tie rod are all pointing at the same point. So you have this instantaneous center over here. So this tie rod is pointing over here. There's no line there. I'm not sure why there's not a line there, but yeah, this is zero bump steer. So this imaginary line drawn through these outboard mounting points and through these inboard mounting points should also go through the tie rod ends. Now, because of Ackerman, we're probably going to move this point inboard. Or if your tie rod is in front of your upright, you would want to move that point outboard to kind of still stay on that same line going through the center of your rear axle. But it is perfectly valid, and actually most cars do this, where you preserve this same length. This tie rod here, this length is the same as this length. You preserve that length and you still have the same axle, still on, or I'm sorry, same axis, is still on the same line, still pointing the same way, but you just move the whole thing inboard. And that will still preserve your bump steer. But what you don't want to do is have a tie rod, like this is the correct length, but it's at the wrong angle. Or if you had a tie rod that was the correct angle, but instead of terminating it here, you said, well, my rack, my steering rack on my car is only so long, so I'm going to have that point here. Or my steering rack is really long, so I'm going to have that point here. The length of your steering rack needs to jive with the length of your tie rods. So if you are determining where this point is based on how long your steering rack is, you can play around with the height of your tie rod to try and get that to match up. And when I say that, I mean, if you had a really narrow rack, then putting your tie rod down here might work if your rack can reach out to that point. If you have a really long rack where, say, the end of it is here, well, you would go up to this line and go, okay, well, my height needs to be there. Okay, so there's bump steer, U-joints on your steering shaft, because the input angle and the output angle, a U-joint don't match up very well when you have them when you actually have this, say, this angle here, that looks like it's about 30 degrees. So look at this here, 30-degree shaft angle. So this is the output, this green trace, as your input shaft is turning at constant speed. So because of these weird phenomena, actually it's not really all that weird, but because of this phenomena, I would suggest if you used U-joints in your steering shaft, use 2 of them and put them 180 degrees out of phase, such as this one. The force is coming this way. Well, this U-joint is kind of opposite this U-joint. So the speed up and slow down of this U-joint will actually counter this one. Or you can buy a double U-joint like this. Steering rack, I kind of just went over this a minute ago. If you have the outboard points of your steering rack, or say you have a very narrow steering rack like this, and you decide to extend it, say it comes out all the way to here. If you don't support this point out here, and the only thing supporting, or the only thing keeping this rack from moving up and down or back and forth, when I say back and forth, I mean along the length of the car longitudinally, the only thing preventing that is these 2 mounting points here. Unless that's attached to unobtainium, and this rack is made from unobtainium, this point over here is going to move around in ways that you don't want it to move around. So I would suggest linear bearings like this at those points out here, or even something as simple as just a tie rod into the rack is going, or not a tie rod in, but a pillow block or something out here for it to go through. I've only seen this once, but I will still say it because I fear that another team will show up with this. But a few years ago, I will not mention their name, but a team showed up with a worm gear reduction in their steering system. And worm gears are a one-way affair. You can put torque in here and it turns this gear, but this gear cannot turn this gear. So that means there is no self-centering to that steering system. There is no feedback. There is no, I want to do this, let me do this. It is, you turn the wheel and you have very little idea of what's going on at the wheels. Unless you can see where they're pointed or just kind of feel which way the car is going, you don't really know which way they're pointed. So do not design a steering system with a worm drive in it. I will not pass your car an inspection. I accidentally did it once, and I watched that car go all over the place on the track, and they couldn't keep the car going in a straight line. But the car did finish the race, but it's not a good idea. The steering stops. They're going to prevent binding in your system, which you don't want to have. It can wind up damaging parts. They're going to prevent the pinion gear in your rack and pinion from hitting the flat part of the rack, the part of the rack that doesn't have teeth, and that is bad for your pinion gear. And also, we don't want your tires to contact stationary parts on your car, like the frame or your fairings or various other parts that your tires are near. If they can steer more than they're supposed to, then they can wind up hitting that stuff. And then you wind up rubbing maybe the sidewall of your tire and winding up with a flat. Most common methods of doing steering stops is actual collars on the rack, as in, right, like maybe under this bellow, actually put a collar around that shaft that would hit the housing and prevent it from going any further in that direction. That is, I would say, my preferred method to see. Or you can have where the rack actually hits a stationary surface. And I've seen that on some catamaran cars where they'll have the steering rack, the end of it, before it kind of disappears into all sorts of linkage going everywhere. Something actually hits some stationary surface on the car. A protrusion on the steering shaft that contacts a stationary surface, as in, as the steering shaft rotates, it has something sticking out of it and it hits a stationary surface. But that only works if you have less than one turn lock to lock. That's not really reasonable for most cars unless you have very lightweight steering. Okay, so sound engineering practices: don't have rod ends and bending, use double shear. I'm sure you've probably heard that before. Test before you come to competition. Don't let your suspension travel enough in droop. And that means it's the opposite of bump, as in when you lift up your car goes over a jump, or the inside side of your car in a turn drops down as the car lifts up because of weight transfer. So in droop, don't allow your springs to unseat. Pay attention to the range of motion for rod ends. They're typically in the 15 to 18 degree range unless you buy special rod ends. Test before the competition. If you use bell cranks, ensure that all elements feeding into those bell cranks and the bell cranks themselves are all in the same plane. You don't want to have push rods or pull rods acting out of the plane of the bell crank. It's going to put weird forces on the bearings holding the bell crank. Think about all forces the component is going to see. I'd say read and note the rules. That's kind of something for every competition. Use a reasonable safety factor and test before the competition. So make sure you test before the competition. I think we've run out of time, but yeah, we have definitely run out of time. Is Brian still here, or did you go to the other session?
Brian went to the other session.
Okay, good.
I have not. I thought I should give it a try today because that's the only reason I don't want.
I hear somebody
to
talking,
leave it here
but I can't
for you.
quite see what
It's like-
they're, I can't understand them. Are they asking a question?
I think it was just somebody's background noise.
Okay. Just here's some examples of suspensions I've seen that. Okay, so that's your upper A arm. That's a spherical bearing, an upward side there. So that's kind of the opposite of a tie rod end. The linkage here where your shock, this is the shock, and then the bell crank. And that hits nice and far outboard. So that's a good thing. There are designs where you can actually have this linkage attached to the upright itself. That gets a little challenging, but it has been done. Oh, I put this on because here's an example of just simple steel welded chromoly tube. This looks like it's probably 3/4 inch tube. So it doesn't take very large tubing. You can actually make a relatively lightweight arm out of steel. It's not some super fancy, super whammadine, ooh, it's carbon fiber, but it works. Here's aluminum billet, machined A-arm. This works too. It does have a tie rod on the outside here, but note that that is not the same A-arm that the shock is mounted to. So that's perfectly valid. However, it looks like they might have a tie rod down there. That's not as valid. Okay, so this is a suspension that I have a few issues with, so I'm going to go over those. I think this was kind of a first year attempt, and this team has learned from this, but as I pointed out earlier, your upper A arm should tilt down as it goes inboard. This is tilting down as it goes outboard. So this is going to have positive camber gain, as in this point here, as it swings upward, it's going to move outward. At the same point that this point, as it's swinging upward, is going to be moving inward. So you're going to wind up with the wheel tilting outward. This A arm has a bend in it here, and that's just going to weaken it. They did that so it would come in here, and this rod end here would meet at a nice straight angle. But if you're going to put a bend, you could move that to down here. And actually, I'm not really a fan of that either. I like just going in straight, but that's just my thing. I do like how they have this in double shear. This shock is nice and big, it's meaty, but if you're going to have something this meaty, which is kind of over-engineered or overdone, it might be good to locate this somewhere else and use a bell crank so that you don't wind up with something like this. Like this is a very cantilevered, it's got a lot of torque on this frame tube. So this frame tube, I'm pretty sure this is meeting mid-span. It's not near a node, and you've got this decent length moment arm there. This is pretty far away from this end over here, and part of that is probably driven by just the size of this shock. So there's a few things going wrong here. So priorities: minimize scrub, use zero toe, use zero static camber, make the car track straight easily by using a little bit of caster. Definitely have zero bump steer. I probably should have put that further up in the priorities. And make at least camber and toe adjustable. Okay, and that's just the ones I've already gone through. Are there any questions?
I guess one question that I had was, you were talking earlier about like the friction being very hard to quantify in your system.
Yeah.
If you are trying to, critically dampen your suspension, how do you properly, and I know you gave one metric of multiplication in the common ones used in vehicles to get your ideal springs. How do you, I guess, do that kind of modeling analysis there? I guess not an in-depth walkthrough, but maybe a point in the right direction in order to compensate for that friction within the joints that might.
Well, the friction that I was talking about was more in your steering system, not so much in the joints for figuring out like your damping of your springs. I think that what I'm not sure I understand your question, but I think that you're asking, how do you quantify the friction in your system for factoring that in as a damping force when you're sizing your damper to your spring? Is that what you're asking?
Yes, basically, yeah, basically, I guess.
I don't know. I've never really considered that. I kind of think of the amount of friction in the system is generally low enough that it is nearly insignificant compared to how strong the spring is and how strong the damper is. I don't know if that's a valid assumption, but I would hope it is. Evan, do you have any input on that? Is Evan still here?
Yeah, I'm here. I think I would agree with that. Like in general, your friction of all your joints should be low enough that it's not going to have a major contribution to how it functions.
Yeah, I would say unless you build a suspension that has binding in it, then it shouldn't really matter. And we have seen suspensions with binding in them. I don't want to point fingers. Well, I'm not sure if I should mention the team's name or not, but as recently as 2018 in Hastings, we had a team that had an over-constrained suspension. And basically they had 4 mounting points on their lower A arms and 3 mounting points on their upper A arm. This was their rear suspension. And the 4 mounting points on the bottom, as the upright moved into bump, it dictated not just, well, the lower A arm didn't just dictate kind of the lateral movement of the upright as it typically would, but it also dictated how the upright was leaning fore and aft. It kept it going straight up and down, exactly straight up and down. Well, in theory, straight up and down. And then you have the upper A arm. It has 2 inboard mounting points and 1 outboard mounting point. And that outboard mounting point also tried to draw through a very determined, like a very set arc. And that arc that it was drawing through did not match up with where the upright wanted its top mounting point to draw through, if that makes sense. So
A little foggy, but I think I get where you are right now with it. Yeah.
yeah, it was just it was an over constrained suspension. And because of that, you could actually, like in scrutineering, like I could press down on that corner of the car. I could press down on either back corner of the car. And they even had a little bit going on in front of their car, but I could press down on the back corner of the car and it would just stay down. It might return a little bit, but it would not go back to 0. And if you picked the car up, sometimes like it would just kind of stay there, like up high. So there was definitely some binding going on. I would say make sure you don't over constrain your suspension. If you do feel like you have some friction in your system, then it might be more parts choices, such as, are you asking a tie rod end to bend to an angle that it's not supposed to be bending at? And not just like, and when I say that, you might imagine that I'm saying having a tie rod end that rotates up to 18 degrees and your suspension, as the arm rotates up and down, it sweeps through 18 degrees of motion. I'm not so much saying that. I'm saying if you rotate that tie rod 90 degrees and now you have that for some reason, say it's on a steering tie rod and you've moved your rack backward for some reason. So it's tracing this angle going forward to your uprights and you're right at, say, 19 degrees. You've got that tie rod really bent, or that rod end like kind of past its motion. Now, anything you do with that tie rod, it's going to be binding up. It's not going to want to move right. So even just moving the car up and down like that, you might get some stick. So yeah, check rod ends, check, like I was saying earlier, where actually it might be faster to exit out and go back in. Where is it? Here. Like if the bolt's going through, if the bolt going through here doesn't line up with the bolt going through there, because say maybe they're both attached to a frame member, and that frame member has nodes supporting it way out here and way out here. So cornering forces are actually flexing that frame member and causing the 2 ears supporting this to point kind of more angled this way rather than this way. And same thing for this one over here. Instead of pointing perpendicular to this line, they're pointed more that way. I'm exaggerating, but they're pointed in the wrong orientation. Then you're going to wind up with those 2 axes not lining up, and it's going to bind up. So there's many ways you can wind up with binding up suspension. And sometimes like the traditional way of figuring out if you've got binding in your suspension is to just jack up the car, disconnect the springs, and just move the suspension through its motion. Just pick it all the way up into bump and drop it all the way down and steer your suspension a little bit and do it again and make sure it works at all steering angles and there's no binding anywhere. But that will not expose the binding that happens because your frame is flexing. So sometimes you just have to kind of theorize, oh, I wonder if this is going on there.
My biggest advice probably for teams in suspension that I don't know if we've touched on directly is like both in your design and your manufacturing and testing, try and minimize any slop or binding of the system. So if you have slop, like your vehicle is just not going to behave as it should. It's not going to be as controllable. We see that a lot of times in steering systems where you get slop, but I've also seen it in suspension systems where there's just parts that don't fit tightly enough to each other. That's too loose, or things aren't properly tightened coming into scrutineering. And then binding to that point that Bill made on disconnecting your shock and just testing it through its full range of motion. Make sure nothing's hard to move when it should be free moving. And see where it's what are the stops of your suspension up and down? Is it your shocks, your nice rubber bump stops on the shocks, or you definitely wouldn't want it to be like a hard metal point where you're gonna put your system into bending or some unexpected load that could cause a failure.
Thank you.
No problem.